All right, we should be live. Let me just double check that TikTok is picking up my chat box. We good to go. Howdy, howdy, everybody. Hope everybody's having a good day. Long names need to be abbreviated, so message visibility. Maybe I hide avatars. Maybe I hide timestamps. And then we will just want to try something, y'all, and I'll get to answering questions in just a moment. Oh, that might be better. That might be much better. Some people still have absurdly long names, which I can't help. All right, let's answer some questions. How long have you been studying physics? Well, I mean, I went to 4 years of undergrad, 2 years for a master's, 5 years for a PhD, and then I've been working, you know, doing mathematics and physics since then. And it's been about almost 4 years now, actually, since then. How could we theoretically produce antimatter for interstellar vehicles? Well, we can make antimatter already. We make it in fact, we have antimatter production facilities at particle accelerators. The thing is there's no feasible way that we know of yet to make antimatter in large quantities and to keep it around and keep it in a bottle for long enough that we can use it. It doesn't last very long and we can't make very much of it. We have our first super chat today from Texas Panhandler. Yo, Blitz, happy Wednesday. If I stretched a rope from the Earth to the moon, made it taut, then it tugged on Earth, how long would it take for the tug to be felt on the moon? So that kind of thing transmits forces at the speed of sound. So we would just have to go figure out what the speed of sound is, or the speed of wave transmission is in the rope. I guess for a rope, typically the speed of sound, or the speed of transverse waves is something like what, the tension divided by the Young's modulus or something like this. I may have gotten the units mixed up. It might be the other way around, but yeah, it's going to depend on the speed of sound. So it just depends on the rope. It depends on the thickness, the material, etc. What about a gravity drive? Is that possible? Well, I don't know what you're proposing that would be, but no. Doesn't sound like it. Doesn't sound like the kind of thing that's possible. There's more hydrogen atoms in a single water molecule than stars in the entire solar system. True. Is reason metaphysical? Maybe. It depends on what you mean by reasons. What do you think about dark matter being condensed space? I haven't heard that idea. How tall are you? I am 9'6". What's the next feasible type of propulsion for rockets? Well, probably the most, I mean, chemical rockets are really, like, they're really good for getting us up into space. The issue is how to travel once you're in orbit, how to leave orbit efficiently. And the best way that I can think of to do that, which isn't particularly efficient for large things like people, would be ion thrusters, and we already have those. How should a layperson view superposition entanglement that isn't, bro, we're in a simulation? Well, superposition is not merely a quantum thing. Superposition happens for all sorts of wave phenomena. So if you imagine that you play two different strings at the same time on a guitar, the sound wave that's produced is in a superposition of the sound wave produced by one string and the sound wave produced by another string. Entanglement is a little bit more weird, but it's just a correlation. It doesn't really imply anything about a simulation. The way to think about it, and this is only an analogy, it's certainly not perfect and it misses some key important details, but imagine that you buy a box of shoes, or like a pair of shoes rather. If somebody takes the box before you look in, takes out one of the shoes, and then runs 100 million miles away, and then you open the box, you automatically know what shoe they have. Because you know what shoe you have. What are the most common misunderstandings of physics? Probably anything to do with quantum mechanics. That'd be my guess. Have they actually delayed the launch of Artemis? That's what I've heard, but I'm not really keeping up with it. What's your best analogy for the Higgs field? Well, the one that I use, and it's pretty common, is just think of it like molasses. And that molasses interacts with some things and it doesn't interact with other things. And so things that it doesn't interact with, like photons and gluons, can just pass right through unimpeded. Things that it does interact with, think of it like quarks and leptons and so on, they are going to be impeded a little bit. It's not a perfect analogy, but it does convey that it doesn't have to do with the Higgs boson per se. It has to do with like the field itself being ever present. We have another super chat from Texas Panhandler. Can we get someone to unplug and plug the simulation back in? Probably not. Sorry. What do you think about the Fermi paradox? Also, what kind of hair treatment do you use? Well, the Fermi paradox seems like it's well answered just by recognizing that the universe is really big. Stars are really far away from each other. Like, we think of like, oh, it's just like the nearest star is, oh, just 4 light years away. That is astoundingly far. That is so far. And our galaxy is 100,000 light years away. Or across, rather. Like, the universe, space is so mind-bogglingly big. You just can't even conceive of it. And what kind of hair treatment do you use? I use conditioner and I use shampoo. Get them from the drugstore. Did you ever use Qiskit in your research? Nope, I have not. How does one begin to learn more about advanced physics? Everything I learned is so fascinating. Well, the most direct way is go get a job in, or go get a degree in physics. That is how it ends up happening for most people. That said, if that's not your style, then you could always pick up some pop-sci books and go into a little bit deeper, kind of more sophisticated pop-sci books. I would recommend there's a series by Sean Carroll called The Biggest Ideas in the Universe. It's pretty good. From Garba Gaiman with the 5 Canuck bucks. Thank you so much, Garba Gaiman. I'm so glad that you were there for the Epstein Science Bro last night. No notes. That was a crazy conversation. What's stronger, the strong nuclear force or friendship? Well, look, the strong nuclear force gets stronger the further away you get. Friendship gets weaker. Can you explain why I'm 5, why we think there's dark matter versus we have calculated gravity wrong? Well, look, so it would be very weird. The most simple explanation is that it looks like we see gravity where there's no matter. And it would be very weird if we were just doing gravity wrong, but like somehow there's still gravity even if there's no matter there, right? That's the weird thing. That's something that we see. We see matter where there's where we see gravitational lensing, which is a kind of gravity, where there should be no matter. That's unusual. And that lines up with all of our other observations if it's indeed dark matter. A question I've been wondering about for a long time is, can AI actually advance physics or not? It hasn't yet, at least not as an independent researcher. I mean, it's like used, like particle physicists use like machine learning and stuff like that to like find patterns in data that they may have missed, but that's not like That's not like AI is advancing physics. From Bacon and Bush with the $20, love to see Ask a Physicist. I don't have a question. Oh, well, I appreciate you regardless, Bacon and Bush. If you had to position Earth somewhere else than our solar system, where would you put it? Our solar system's a good place, so I would just put it in another identical solar system, I guess. What do you think the size shape of the universe is? Infinite or finite, unbounded in some shape? It would be really nice if it was homeomorphic to a 3-sphere, but it seems like it's flat. It seems like it's spatially flat, which would lead me to conclude that it's infinite. From Atomic Aerials with $5, are the 2 5-mile tunnels of LIGO truly straight, or do they curve with the ground and operators compensate for that? How do they compensate for that? No, they are truly straight, which means that they actually have to, they're actually at, like, the middle is at a different height than the ends. It's lower, in particular, because you can't compensate with, like, light. Light travels in a straight line, right? So Simi, thank you for the galaxy. Is extraterrestrial life likely to be discovered in our lifetime? In some sense, it may already have been. There was this announcement by NASA a few months ago that seemed to indicate that they had, like, compelling reason to think that life at one time existed on Mars. Do you think nuclear fusion for energy production purposes is ever going to be feasible? Yeah, I kind of think so. Oh. How does the Earth is put on the exact place to have life on it? Coincidence? No, it's just if the Earth wasn't in the place that was suitable for life, then there wouldn't have been life here. Do you know who Evidence First is? If so, what do you think of him? I don't. How do we know the age of a galaxy? By a residual radiation. I don't know what you mean by a residual radiation. In fact, I don't know the mechanism that we use to figure out the age of a galaxy. It's not even clear to me that that's a meaningful term, right? Because, like, if you have a galaxy that forms and then it merges with another galaxy, is that a new galaxy? If it's not a new galaxy, then which galaxy do you take as the galaxy that gives it its age? If it is a new galaxy, I guess that's a fine mechanism that you could use, but, like, I don't know, it just seems kind of weird. It seems kind of weird and arbitrary. What do you think about putting servers on the moon? Is it possible or just wishful thinking? Why would we do that, though? Have a really long latency. We were counting the age since the Big Bang, so we have to figure it out somehow. Well, we don't have to figure out how old galaxies are. We just need to figure out how long ago the Big Bang happened. Right? What's happening inside a black hole? At this point, we don't really know. Like, there's a lot of good guesses, though. If I went 60 miles in 1 hour, how many miles per 2 hours? You're moving 120 miles per 2 hours. If we were moving at the same rate. Is it possible for light to bend back to us due to gravity from other bodies of mass in the universe, allowing us to see into our distant past? That is in principle possible. You would need you would need it to whip around a black hole, or you would need a series of galaxies that make it do a big bend. But we would never be able to tell because we can't resolve things as small as the Earth from that far away, because it would be that light would have traveled a very, very far distance. Delivery from TikTok, I think. It wasn't announced. I just heard that other people got it, so let's do a unboxing really quick, just make sure what it is. I think it's just a mug. Yep. Or a thermos, like one of these. I don't even know if it's a good one, but here we go. I guess. That's kind of nice of them. I don't know why they sent it, but cold beverage only. Remove sticker before using. I want to put a hot beverage in it, though. Kind of a shame. Okay, well, that aside. All right, let's answer some more questions. Did I just show the label? Oh well, I'll just clip it out. No, this isn't TikTok Shop. This wasn't a TikTok Shop thing. This was a TikTok creator thing. They just sent it to a whole bunch of creators in the education program. I didn't ask for this. Right. How sure are we that the Big Bang happened or it's the accepted theory? Well, we're sure that it's the accepted theory. As far as how sure are we that it happened? I mean, like, insofar as that's the accepted theory, like, people are pretty confident that it's the accepted theory. In the education program, yeah. So TikTok has different niches. So TikTok pays for, like there are different niches for, like, the type of content that you produce. I make educational content, right? That's what I do. That's what the videos I make that's TikTok, generally physics explainers and debunking stuff. And so that puts me into the education niche, and they have, like, certain monetization schemes if you're, like, in different niches. And so I'm in the education part of the program. So I mean, you know, it's just how it works. Sorry, I have to scroll down a little bit. If light photons have no mass, how is light absorbed by a black hole? A question I've always had. Well, gravity doesn't only affect things with mass. Gravity affects anything moving through space-time. The curvature of space-time is caused by mass, energy, momentum, stress, pressure, and that curvature affects the trajectory that anything traveling through space-time occupies. So yeah, it doesn't have to do with mass. So your only career choice is college teacher? I mean, not necessarily. Can't wait to start. Fontanot, I hope that your healing happens quickly. How does centrifugal force work? This is a really good question. So despite what high school teachers are going to tell you, centrifugal force is not fake. Centrifugal force is a real thing. It's just a frame-dependent thing. So the idea behind centrifugal force is that, generally speaking, say that you're moving in a circle for whatever reason. Maybe you're tied to a string, and that string is, so you're being brought in a circle by that string around some central point, and you're spinning around it. Maybe you're orbiting something, whatever it might be. There's some force keeping you moving in a circle. Now, Newton's first law is that an object in motion stays in motion unless acted upon by an external force. Now, what that really means is that an object in motion stays in the same motion, meaning that the velocity stays constant unless there's an external force. And so what this means is that if you are moving in a circle, from your perspective, moving in a circle, there will be something trying to keep you going, trying to keep your velocity unchanged, trying to fling you out. That is the centrifugal force. That's what's pushing you up against the wall, say, if you're in the, you know, that Gravitron or whatever it's called, that theme park ride. Basically, the centrifugal force is your body trying to move in a straight line, but something preventing you from moving in a straight line. From Sean Paul with the $20. Thank you so much. Sean Paul asks, I watched your reel on photons warping spacetime. In it, you referred to an Audi tachometer as a speedometer. As a car guy and nerd enthusiast, I'm extremely disappointed in you. I hope you will issue a public apology. I won't, but it did drive engagement. Also, I don't know anything about cars. From Ryu Zen, with the 100 Indian rupees, do you work as a professor in a university? I don't. No. Can you give an intuitive explanation of exterior algebra in terms of how it is useful in GR? The only way it... Okay, so the only way it really shows up in my experience is really just insofar as the exterior differential operator is a relevant object that you can use to build curvature constructs or curvature invariants and things like this. I don't know what you mean by like how it's useful. It's just a part of differential geometry. Or at least that's how it's used in GR. It's used in a differential geometry context. And so you can talk about closed things, you can talk about exact things, and the difference between those can give you information about topology. You can talk about, you know, irreducible decompositions so that, you know, you can have components that are symmetric, components that are anti-symmetric when you take a covariant derivative. In the anti-symmetric piece, when you have a metric compatible connection, or a torsion-free metric compatible connection, those anti-symmetric pieces of the covariant derivative of a one form are going to be the exterior derivative of that one form. So like there's a lot of ways that it shows up. I'm not really sure what you mean by useful though. Like the exterior derivative just is present all the time. But other than that, we don't really worry about the algebraic structures, or at least I don't. Was entropy in the universe before the Big Bang high or low? Or in other words, how is the uniformness of the pre-Big Bang different from the uniformness of the heat death? Oh, well, so the early universe entropy was very low. That's the idea. And the reason for this is essentially gravitational. And this is like speculative, this is frontier stuff. But the idea is that like it was uniform, but the gravitational, the entropy associated with space-time, not just the distribution of matter, but the entropy associated with space-time was astoundingly low. That's the idea. How do photons have kinetic energy if they have no mass? Doesn't that break the formula? The formula only applies to things that are moving at slow speeds. The relativistic formula is a correction of that, or a modification of that, and it's just different. The 1/2 mv squared only applies for, you know, non-relativistic things. From the undead Fermi with 140 ZAR, I have a friend that claims quantum computers aren't real because qubits aren't particles. From what I could find, this isn't true, but what exactly classifies as a particle in this context? You don't need to have a particle in order to have a qubit. Qubits and particles are not necessarily the same thing. Now, if you had extreme control over individual particles, then sure, you could make qubits out of them, but that's not how we generally make qubits these days. Is the universe an infinite flat plane, or is it a sphere so large that our portion of the universe seems flat? Well, it's not a plane. It's three-dimensional, kind of obviously. But we currently can't tell the difference between it being infinitely large and spatially flat, or it being of just an enormously large three-sphere. This is the issue that flat earthers have. From Edrapandia with 10,000 IDR. I don't know what IDR is, but thank you so much. What if photons have a mass of 1 because they move at c? Mass of 1 what? How does one create qubit entangled particles? How do we know they're entangled without measuring? So I don't know how modern quantum computers create qubits. That's not in my field. It's not something I've read much on. However, what I do know is a way that we can create entangled particles. One of the ways that you can do this is you can take a photon and put it through something called a nonlinear optic. What nonlinear optics do, at least what some nonlinear optics do, is it will take light of a certain wavelength and a single photon, and it'll spit out 2 photons with double the wavelength, half the energy. And those photons will have certain polarizations, and if you filter out all but certain polarizations of those 2 photons, like if you filter them out so that they come out along a certain axis, then you can guarantee that those 2 photons that come out are entangled even if you don't measure them. Just because of that's the way the quantum mechanics works. How would the difference between flat space or large sphere be tested? With just better and more precise measurements. That's the only way that we could tell the difference. From G073NKS with the $5, how far away would a supernova have to be before the light from the supernova would arrive before the neutrinos that get released before the collapse? I don't know off the top of my head. That's something that we could in principle calculate. it basically just depends on the, you know, essentially like how much faster light travels than neutrinos. And neutrinos are very, very light, so they're going to travel like very, very close to the speed of light. And we would just have to work out what percentage they are, what, like how many, like 1 part in 10,000 is the difference between their two speeds, in which case you would probably expect, you know, whatever the initial delay is. If it's 1 year, if it's 10 years, whatever it is. You would just have to work out the actual calculation. I don't know it off the top of my head though. We have found neutrinos in Antarctica. Yes, we have. Well, they're not from Antarctica. They're passing through Antarctica. If big enough stuff disappeared on Earth, it would make a sonic boom, more or less. If the entire Earth disappeared, would anything like that happen because there's no air and space, but enough? No, not really. Neutrinos traveling under the speed of light? Yeah, neutrinos travel just less than the speed of light. What causes waves to diffract? Are there scenarios where gravitational waves would diffract? We need many more gravitational wave detectors to see it. So, it's a good question. The question about, so diffraction occurs whenever you have reflections, whenever you have barriers that stop the gravitational waves from passing. The thing is, it's not clear to me that there's any medium that can change the rate at which gravitational waves move. I suspect the answer is probably not. Actually, that's probably not true. It's probably not true, but I also don't know if that's been calculated. And the reason I say this is because, for the most part, space is basically empty. So gravitational waves are going to travel from point A to point B without passing through anything all of the time, basically 100% of the time. And so the issue is that, like, there's not a medium for the gravitational waves to slow down in or to be reflected off of. That is really relevant here. Now, what causes waves to diffract is literally just reflections and boundary conditions, essentially. So you have waves that bounce around, and so if they can't pass through a barrier, they will either be absorbed or they will be reflected. And that reflection can superpose with the other propagating waves in the other direction, and that will change the behavior of the waves. The waves add up, and so you get a different wave resulting from the barrier being present than if the barrier wasn't present. You could also think of this in terms of Huygens principle. Huygens principle is that for every wavefront, you can think of it as a spherical wavefront, and that spherical wavefront then emits waves in all directions, and then those waves superpose to produce the wavefront that you started with, but it's not a particularly intuitive answer. What's superpose? Superpose just means like overlay, basically. How can current stay the same even after going through a resistor? Wouldn't the energy be converted as heat and losing some of the current? The energy is, some of the energy is converted as heat, the energy being the potential. This is the electric potential energy that's lost. Not current is not the energy. We just got a Cash App. From Noel for the $1, would love to see you demolish Q-Top in a debate. I've done it several times already. But thank you. Do tachyons exist, and how can we detect them? Tachyons probably don't exist in the way that you're thinking of. From Shay with the $2, entropy just isn't what it used to be, SMH. Indeed it isn't. If entangled particles are separated to Andromeda's distance and the lab with the Earth particles moved away at some speed, when does the collapse happen in Andromeda? I don't know what the speed has to do with this. But the point is that it's not even clear if collapse is a thing that happens. Collapse is a interpretation specific view, and under that view they would take the position that collapse happens instantaneously, but it's not even clear that collapse is a real thing that happens. But in an ammeter, it doesn't show how much of a deflection. That's because the current doesn't change. The current has to be conserved. Gravitational waves don't accelerate masses like EM waves accelerate charge. Gravitational waves do accelerate masses, actually. Turns out they do. Which is why gravitational waves passing through matter would, in principle at least, you know, they would interact with it and potentially change speed. Why do neutrinos and light travel at all? This is from C-Bar with the $5. Why aren't they relatively stationary? Well, light travels because it's a wave, and that's what waves do. Waves travel. If it wasn't traveling, it wouldn't be a wave, and then it wouldn't be light. Neutrinos travel because it's hard to make something with zero energy. You have to have zero. If you're going to make neutrinos, you're going to make them with a certain amount of energy. If you make them with exactly as much energy as they have in mass, then they will be stationary. But they have very little mass, and so if you give them even a tiny bit of energy, they're going to be zooming. Why don't we know the mass of the neutrinos? Because it's hard to measure. That's why. It's really hard to measure. Can you explain how acceleration is the symmetry breaker for time dilation? Yeah, I mean, essentially, the symmetry for time dilation is merely that any two inertial reference frames are the same. But when you accelerate, you are changing between inertial reference frames. So you no longer, like that is something that's happening, right? Your inertial reference frame is changing. And so, of course there's going to be a symmetry break, a symmetry violation, if you're changing inertial reference frames and your buddy isn't. Now, are you asking why is it that being in a non-inertial reference frame, are you asking why we can locally determine when you change inertial reference frames? That's because an inertial reference frame is a geodesic, which is a geometrically preferred path. And it's the path things take when there's no forces acting on them. From Oceanus Helios with the $5, do we have any examples of zero energy in physics, or do we only find a minimal energy state as a baseline? Yeah, we don't really have any examples of zero energy. It's not really a thing. Like, energy is typically a relative thing, except for perhaps gravity, but that we don't really know the answer to yet. Why isn't conventional current in the direction of the electron flow? Because when it was determined, when it was made convention, they didn't know that electrons existed yet. We see the potential field in EM, and gravity. Do we get similar potential fields under strong and weak forces? Do those fields fall out of the math as we go from electroweak to EM and weak? So for the strong nuclear force, you can write down a potential field, but it's not that simple because it's strongly coupled, and so it's not like, it doesn't really have a truly classical analog. I mean, you could write down a classical analog, right? The trouble is that, yeah, what's the way to put this? So you can write down the Lagrangian, for a classical Yang-Mills, which is what the weak nuclear force is and what the strong nuclear force is. Like, these are Yang-Mills fields. Now, yeah, I guess the point is that we don't really have, yeah, and then you can write down the equivalent of the Maxwell equations. And I guess that you could get a potential field that way. The trouble is that these are like, well, okay, you could get the Maxwell equations for the strong nuclear force because gluons are massless. The Maxwell equivalent. The weak nuclear force, they are not massless. So the Lagrangian changes. I guess you could still write down the Yang-Mills equations of motion, but they would be different. I'd have to actually work that out. But yeah, I mean, you could. It just doesn't represent what actually happens because they're strongly affected by quantum effects. So you would have like a classical thing that could then be quantized. And then you would end up with something that looks like the strong nuclear force or something like that. Can you explain why things like energy and momentum are conserved quantities? Well, that's to do with Noether's theorem. So if you take a system, the way that we describe systems, at least kind of in fundamental physics, is we use a Lagrangian. A Lagrangian is you can think of it as a number that kind of assigns to any trajectory that the system takes through configuration space. Well, I guess through phase space. One of those is the correct word. It assigns a number to those. And when the Lagrangian changes, when you do a symmetry transformation, you would say that the Lagrangian is not symmetric under that symmetry transformation. But if the Lagrangian doesn't change, if this number doesn't change, regardless of the path that it takes through phase space or through configuration space, then you would say that it is symmetric under that configuration. And then you can do some math to the Lagrangian, and you find that if you have a Lagrangian that is symmetric under some symmetry transformation, that automatically pops out that there's some quantity associated with that trajectory that is conserved along the trajectory. And that is things like energy and momentum. Man, I'm hungry. Did I not eat enough today? Layman question about relativity. Am I correct to assume that it is acceleration that causes the time difference between two objects moving away from each other and later reuniting? Yes, it is acceleration. From Preston Devaney with the $5, can you explain how it's possible for there to be a first moment of time? It seems illogical for an atemporal state to change into a temporal state. Look, so that only seems illogical if you think of time flowing as like some account of change. But if you take kind of the slice of bread account of change, where, you know, this is like the B theory of the B theory of time. If you take that kind of account of time, then time is just a way of distinguishing different slices and different slices of bread. And then there's just no issue for there being a first slice of bread. The slice of bread being the universe, or the loaf of bread, by the way, being the universe, and each slice being a moment of time. There's no issue in just having like a first slice, right? And it could be that there's just like air beyond it, which is not a slice of bread, so there's no time there. And it's not like a thing changing in time. We're not talking about that. We're talking about like from a outside of time perspective. Oh my God! Every week, it's the leaf blower again. Theoretically, is portal travel possible? If you can make a stable wormhole, I guess. But as far as we can tell, there's no way to do that. How big was the universe at the Big Bang before the math breaks down? Usually, the number given is about the size of a beach ball. Do physicists investigate past physicists' work, or do they just agree with the literature, no questions asked? It depends on what they're doing, but oftentimes, yeah, it involves looking at past physicists' work. That said, what you're probably going to find is, like, nobody's seriously looking at, you know, Einstein's derivation of the precession of Mercury from GR for mistakes, because that's been looked at by hundreds of physicists, that's been looked at by thousands of physicists over decades. So there's just not an issue there. Like, it's reasonable to infer that any issues that may have existed have been caught. But yeah, people look at old things all the time. I think time as we experience it is largely... Okay, that's not a question. The loaf appears... No, that's not a question either. In the cloth analogy of gravity, why does mass have a tendency to move at all? The cloth analogy is just that. It's an analogy. It doesn't really explain why mass moves. Because, you know, the cloth analogy is a two-dimensional representation, a two-dimensional spatial representation of four-dimensional space-time. So it's just, honestly, in my view, it's just not a very good analogy. From David Vermillion with the $5, when black holes merge, how is it possible that two infinite masses can merge? Shouldn't the 2 points never be able to touch since they are infinite? They're not infinite. The masses are very finite. The mass of a black hole is very finite. And there's the leaf blower right in front of my window. Do you consider pi to be 3 or 3.14 ... Well, when I use it, it's just pi. I never really punch it into a calculator. Is the quantum model only a statistical model for electrons based on fixed energy levels? If it is, can you please tell me some physical interpretation for why it is? Is the quantum model only a statistical model for electrons based on fixed energy levels? Look, it's a model. I don't know what you mean by is it only a statistical model? Like, it's a model. The predictions that it makes are statistical, depending on the kinds of predictions. Sometimes it makes very deterministic predictions. I guess I just don't really understand the question. I don't really get why quantum physics and general relativity is incompatible. Can't just quantum superpositions follow the path of curvature of space and everything is solved? Well, look, there's kind of like an intuitive explanation, namely, we need some way to describe the space-time curvature of an object that is in quantum superposition, right? An electron has mass, and an electron is distributed across its entire wave function. It's not located at a single place. So what does the space-time curvature look like? That kind of implies that the space-time curvature itself must be in superposition, and we have no way to actually describe that with our current mathematics. With our current methods at all. What do you think about Penrose diagrams? I think that they're very, very handy. Leaf blower in February must be warm. Yeah, it's 66 degrees out right now. How does special relativity imply general relativity? It doesn't. It sounds like A10 is. It sounds like an A10 is doing a gun run every time Blitz talks. Yeah, it's loud. Okay, he's gone though now. You know. I've heard you say that decoherence is consistent with many worlds interpretation. Do you also agree, however, that decoherence can also be an ingredient in other interpretations of quantum mechanics, like a modern Copenhagen? Yeah, that's how it's usually interpreted. Decoherence is a part of most understandings, most interpretations of quantum mechanics right now. Let's scroll down to the bottom so I'm not behind. What assumption in modern physics do you think is most likely wrong, but we continue to accept because it's mathematically convenient? That's a hard question. It's hard to say that anything is most likely wrong because it's like the math is really nice, and then we don't have any experimental evidence that it's wrong. So it's hard to say. Can you talk about how you found interest in physics? Yeah, so I was like 8 or 9 or something like this, and I started I was Googling around, this is early days of Google Images, with a friend, and I stumbled upon a picture of like a rendering of a black hole. And I was like, that's super cool. I want to know more about that. And so that got me interested in black holes and physics in general and relativity. And then I watched a PBS Nova special on, I think it was called The Fabric of the Cosmos, or maybe The Elegant Universe by Brian Greene. And I thought that was super cool. And so I'm like, I'm going to do that. And so that was string theory stuff. And here we are. What's the concept of the universe expanding and the redshift? Yeah, so the idea is essentially this. Everything in our universe seems to be moving away from us. The faster or the further away from us it is, farther away from us it is, the faster it appears to be moving. The way that we can tell how fast it's moving is by looking at redshift. Oh my god, he's back. The redshift, what redshift is it's kind of like the light equivalent of when an ambulance drives by you and you can hear the tone changing. When it's driving towards you, it's higher pitched. When it's driving away from you, it's lower pitched. The faster something is moving away from you, the redder the light it emits looks. If it's traveling close to the speed of light away from you, it'll look very red. If it's traveling towards you, it'll look bluer. And the further out we look, the further away that we look at things, the redder they look, which means that they're moving faster. So, or at least it implies that they're moving faster. We can infer that. So the question then is, why does everything seem to be moving away from us? And why is it that the further away something is from us, the faster it appears to be moving? Well, there's two explanations. One, it could all be a big old coinkydink, or it could be that the second one is that the entire universe is expanding. And so it just looks like it's expanding away from us, but really it's just because the distances are growing between everything, everything looks like everything is moving away from it. And so that's how we come to that conclusion. And I'm hungry. How does one come up with mathematical equations when studying something unknown? Sometimes it's just guessing. Sometimes it's looking at data and trying to fit that data. Sometimes it's using using some like intuition or some elegance or beauty-based argument. It really depends. They come out of nowhere. From Johnny Carter with the 5 New Zealand dollars, off topic here, but I love how you keep crushing flat earthers. Keep it up. Well, I appreciate you. Appreciate you, Johnny. Will we ever build a non-combustion engine powerful enough to break away from our atmosphere? Maybe. There's not one single video of a rocket taking off and breaking the atmosphere. Why? Sure there is. Look up the, what is it? It's called the Mesos. Let me go pull it up really quick. Look up the Mesos amateur rocket launch on YouTube. It's an amateur rocket launch showing the entire video the entire time by Kip Dargados. How much is the Democratic Party paying you to spout this misinformation? Misinformation like science stuff? So are you on record saying that the Republican Party is against scientific information? Because, look, you said it, not me. What's your opinion on Greek schools? Some schools get books 2 to 3 months late. I mean, I don't know anything about that. Seems bad. What is helium-3 used for? And are people saying we could, what does this say? We could mine it on the moon. So helium-3 is a likely fuel for fusion, or fusion reactors. And so you would want it if you're going to try to produce energy using fusion. Is it worth it to learn calculus? I would say so, yeah. Martin Kowalski, I don't have an answer to your question. I'm not deep in algebraic QFT. I do relativity stuff. What's your favorite thermodynamics formula? Probably Boltzmann's formula for entropy. That entropy is proportional to the log of the number of microstates. That's really nice, but that's more like statistical mechanics, I think. From Oceanius Helios, with the $5, we stand on the shoulders of giants. But Dr. Blitz, which physicist do you feel is your spiritual guardian, or the one who inspires you the most? Does it count if they're still alive? Roger Penrose is definitely up there. Albert Einstein's definitely up there. Those are probably the two biggest. Is upside down gravity possible? Well, then it wouldn't be upside down. It would be right side up. I just talked to a professor of mine today. I'd like to know your opinion about crank physicists. That they waste the time of themselves and of physicists. What do you think of the GRW theory of quantum mechanics? Look, I haven't read a whole lot into it. I think it's actually at least testable. and I think that running tests to see if it is true is worthwhile. I suspect it's probably not right, because it'd be really messy if it were, but maybe it is. What do you think happens if something goes faster than light? Well, you've broken the laws of physics, so you may as well just make it up. Do you consider gravity to be a force? Yeah, I think it is. Insofar as anything is a force. A force is, stealing this from Quantonaut, a force is anything that can cause momentum transfer. In which case, gravity can certainly do that. Secondly, all of the fundamental forces that we know about, the strong force, the weak force, and electromagnetism, they all involve the curvature of something. They just involve the curvature of something called an associated gauge bundle. Or sorry, a principal gauge bundle, which has an associated bundle. A principal gauge bundle, and like, fine. It's just a curvature in a different thing. What scientific phenomena do you want to be real but don't know if it can be? It'd be cool if wormholes were real, right? But I don't know if they can be. Why are we imagining forces? Who's imagining forces? Are the Einstein equations globally well posed? Well, they are globally hyperbolic. That's been proven. I was looking into this yesterday because I was looking at a modification of the Einstein field equations to see if I could get global hyperbolicity, and it seems like I probably can't. I modify them dramatically. If by well posed, do you mean that they never end in singularity? Probably not, but that's just because they're nonlinear. Or insofar as singularities are like a generic outcome of GR. From a Dwayne Warren with the $2, would railgun tech work for launching UAVs into space? Probably, but they would have to survive like thousands of Gs, right? Why are all the orbits in a flat plane and not at different tilts? Well, they are at slightly different tilts, but it is basically the same, you're right. And so the answer to the question is essentially it's a result of conservation of angular momentum. So the ball of gas that formed our solar system did have an overall net rotation, which is why the sun is rotating and why all of the planets are rotating and in the same direction as the orbits are moving. And it's just because all of the other motion basically canceled itself out except the overall motion associated with the angular momentum, and that's what was left over. Opinion on Carlo Rovelli. Well, I haven't met him, but he seems like he's pretty good at his job. But I'm confused. Just because we haven't seen something faster than light doesn't mean it doesn't exist. Aren't there smaller particles than photons? Surely they could go faster than light. Or no? Well, look, one of the laws of physics that we have, the principle really, is that nothing can go faster than it. Now, things with no mass seem like they have to go at the speed of light. Things with mass seem like they have to go slower than the speed of light. That's relativity. You can't I mean, like, if you want to say that perhaps we're wrong about that, then sure, but then you're just in the realm of sci-fi, right? Binary Ghosts with the $5. What is an example of 1 Newton of force that a person may encounter in their everyday life? The weight of an apple. Coincidentally, an apple has a mass of around 100 grams, your average apple, and the acceleration due to gravity is about 10 meters per second squared. So it's about 1 Newton worth of force, the weight of an apple. Does the moon's gravitational pull have any effect on our biology? I don't know. It seems like there might be some things that are synced up with the moon's phases, but it's not clear if that's a result of the gravity. Is working with formulas that include air resistance complicated? It can be, but often not. You can always at least solve these things numerically. Where does that principle come from? Just empirical observation? Yeah, basically. Is every point in space the summation of every EM wave in the universe? Well, the points in space aren't EM waves, so I don't know what the question means. Do you answer any questions from chat? If so, what did you study to get here? I studied physics, and math, and then more physics, and then more physics, and now we're here. From Chase with the $10, I'm deriving a novel function that predicts the max order for which alpha vectors of a string theory will produce non-redundant gauge groupings using dimension, SUSY, and layer as parameters. Any tips? Bro, you're the string theorist, not me. You're the string theorist. This is your field. At least, well, that's your field. I got nothing for you. I'm a GR guy. Don't make me do string theory, please. I don't want to. I'm afraid of it. Very hard. Most useful physics principle you wish laymen understood. Energy conservation would be good. Like really energy conservation, including potential energy and stuff like that. Be really good. If general relativity's equations change qualitatively once quantum effects are included, it suggests that gravity and quantum mechanics are much more deeply entangled than classical theory admits. This is not like classical theory doesn't admit this. This is exactly the point about quantum mechanics. Like the classical quantum mechanics fundamentally changes the classical equations that we have. Can AI do math? No, but Python can, and AI can write Python code. We have an ideal gas at temperature T, and somehow we increased its internal energy by giving it some net angular momentum. Would its temperature increase? No. So temperature is a... Okay, well, you've actually changed it by giving it net angular momentum. I still suspect the answer is no, but we're talking about thermodynamics and non-inertial reference frames, which can get a little bit hairy. But classically... Well, okay, actually, here's the issue. If it has net angular momentum, I guess we could just say that each individual molecule is just spinning about its own axis or something like this. Faster. In which case, I suppose it could. I suppose it could have more energy. Yeah. It could have a higher temperature. But that would very, very quickly equalize via the that energy that's, you know, captured in its angular motion would very, very quickly thermalize and distribute across all of the modes of internal energy storage. So it wouldn't keep its net angular momentum particularly long. It's actually an interesting question because you would think that it would thermalize. Like imagine they go to 100 I don't know, carbon dioxide molecules. They're all bouncing around, but then you just kick all of a sudden so that they're all rotating. Now, angular momentum would have to be conserved. Oh, so then I guess that they just wouldn't be in thermal equilibrium, right? Yeah, they just wouldn't be in thermal equilibrium. So temperature might not even be well defined. Because thermal equilibrium would kind of require that energy is equally distributed across all of the different modes, but you couldn't because of energy, unless you had some mechanism like the barriers of, like, I don't know, a box of gas or something like this, that can apply forces to modify the angular momentum and distribute that energy evenly. Then no, I don't think that you could have them be at thermal equilibrium. So you might not have a well-defined temperature. How can you tell an object isn't moving? I don't understand the question. It's either moving relative to you or it's not. Do you study pure math outside physics, like Hilbert's problem or stuff like twin primes? Well, I don't do number theory, but yes, I do pure math outside of physics, yeah. How do I know what Gaussian surface to use to find the electric field? This is the kind of thing where you just kind of have to intuit it. You just have to build the intuition to figure it out. You basically want the most symmetrical Gaussian surface that you can find. That's still, or you want the surface that respects the symmetry of the charge distribution that you're studying. Just a quick question: why can't the three-body problem be solved with the Euler-Lagrange equation method? You just can't integrate it. Like you just can't integrate the differential equations. You can write down the differential equations, the Euler-Lagrange equations, or you can write them down no problem. You just can't then solve them. At least not with the finite list of symbols. The finite list of fundamental symbols, I should say. He's reading questions I don't see populating. Well, I'm a little bit behind. Deal with it. Sorry. Or I'm ahead. Oh, you're on TikTok. That's because I'm also on YouTube. The latitude coordinate of the Great Pyramid of Giza, 29.9792 north, numerically matches the speed of light in a vacuum. How do you think they knew this 3,000 years ago? They didn't. 29.9792 is not 299 million whatever. Furthermore, it only matches in one particular choice of units. If you work in miles per hour, or miles per second, the speed of light is 186,000 and change miles per second. And then it doesn't match. From a Dwayne Warren with the $5, is public debate or exposure a physics version of sparing to integrate thinking patterns? I have no idea what that question means. Maybe, if I'm understanding your question correctly, I think public debate, this doesn't even have to be public debate, just arguing with someone about something I think is a good way to come to kind of solidify your ideas. And from Turd Ferguson with the $5, would a photon traveling in the same direction of the expanding universe appear to be moving faster than the speed of light? No, it would appear to be moving slower than the speed of light, actually. Oh, you mean would it appear to be moving faster than the speed of light away from us? Yeah. So the thing is it just wouldn't get somewhere faster than the speed. It just wouldn't. So look, what you can ask is you can ask how long does it take from the time of emission to the time of reception. For example, you could take. Imagine that you have someone with a laser in one galaxy and someone with a mirror in another galaxy. The laser is really powerful. You shoot the laser at one galaxy and then you wait for it to come back and get back to you. It would take longer than you think it would, because the light is expanding in the intervening time. During the start of the Big Bang, where was all the energy? Like, what was it a property of space-time itself? Gemini said the expansion field. So it depends on your view here. If you take the inflation view, then that's what Gemini's getting at, the expansion field. We would call it the inflaton field. It has all of the energy stored in it. Much like how dark energy has some amount of energy stored in it now, it would just have way, way, way more. However, after something called inflationary reheating, that energy is just dumped in the particle fields, and you just have electrons and quarks, or you'd have leptons and quarks, and not quite photons yet, but gluons and stuff all over the place with very, very high energy. Oh, did you study much homology in grad school? Nope. No, I didn't. Probably should have, but I didn't. Can you explain Chern classes? I actually don't have a good intuition for them, so probably not. Maybe I'll put that down as a video that I'll make, though. I'll make a video about Chern classes, just that way then it'll force me to actually develop a good intuition. Does light actually travel like we think it does? Well, yeah. Is it possible you could just disappear if you entered a universe with different fundamental constants, like you could theoretically just vanish? No? But I also don't know how you would enter a universe with different constants. Not all planets rotate the same way. Can physics explain that? Yeah, so almost all planets do. The one exception is Venus, and the only explanation that we can offer is that it was smacked by something really hard in the early universe. Where does the energy of a photon go when it redshifts, given that energy is conserved? Energy is not conserved in a global sense in the universe. That energy disappears. How would light from opposing and identical sources be affected? I don't understand the question. Is the universe really expanding or contracting? It's really expanding. I'd like to see a flat earther go up against you. Lol, easy win for you. It happens all the time. Sometimes the callers talk about 1 is infinitely greater than 0, and normally you say no, 1 is 1 greater than 0, but isn't it infinitely greater because of the decimal system? No, it doesn't really have to do with the decimal system. The point is that they want to talk about multiplicative factors, and I want to talk about additive factors. And this is all to say that, like, this statement that, like, it's that much greater, like, this is like a semantic argument. It's not really like a meaningful argument there. When do you think nuclear fusion will be used as an energy source? I have no idea, but hopefully soon. Why is dark energy slowing and not speeding up? Well, it's still up for debate. We don't know for sure. How do objects going towards each other 99.9% the speed of light not surpass the speed of light? Because velocities don't add the way that you think they do. That only the way that velocities add, the intuition that you have that if we're both approaching each other at 5 miles an hour relative to the ground, then from my perspective you're approaching me at 10 miles an hour relative to the ground. Sorry, from my perspective you're approaching me at 10 miles an hour. That's only a good intuition. That's only a good method, this velocity addition, at low speeds. It's just false at high speeds. Does renormalization imply reality is scale dependent? Not that reality is scale dependent, but just that you expect different qualitative features at different scales. Are you actually a doctor? Well, I actually have a PhD, so yeah. What is antimatter? My friend said it's like an electron that's positive and a proton that's negative. Yep, your friend nailed it on the head. Is the path integral a calculational trick or ontologically real? Good question. That's a question for a philosopher. My view is that, well, okay, it depends on which path integral you're talking about. If you're talking about the path integral, Feynman's path integral for quantum mechanics, I think that might be a calculational trick. If you're talking about the QFT path integral, then I think that might be real. In some sense, they're related, but from Tobias Berger with the 129 Czech crowns, does the existence of the Planck length debunk the man in the well infinite division thought experiment? Why not? The Planck length is not some it's not the smallest possible size. It's not like a discrete size of our universe. The Planck length is just a natural size to describe quantum gravity. I feel like I have to blow my nose. I got a bloody nose yesterday and it was really miserable. Do we power through? Yeah, we power through. So two objects moving at speed of light collide. Well, they can't be moving at the speed of light, but they can be moving close, yeah. Oh, we have a $10 Cash App from Grimlock. Oh, and a $2 from Robert. Robert says, with the $2, thank you for answering my question today. Well, of course, Robert. And from Grimlock, with the $10 for you know what to do. Yeah, it's time for me to waterboard myself. You're right. Are fields like magnetic and electric real or just mathematical tools? At this point, if you asked physicists, it's probably the case that most of them would say that they're real. They have too much utility and too much, I don't know. In some sense, they seem like they're too intertwined in the way that we do physics and the way that we understand physics for them to not be real. Also, in some sense, they can store energy. So that would be kind of weird if they were just kind of like a math trick, right? What's your favorite Taylor series? I don't have a favorite Taylor series. Is it possible for a black hole to lose enough mass to stop being a black hole, or is it a one-way process? Yes, it's a one-way process. If light has mass, how can it move at the speed of light? If not, why does it get pulled into black holes? Light doesn't have mass, but it gets pulled into black holes because black holes, what gravity is merely the curvature of space-time. And photons travel through space-time, so they're going to be affected by black holes, whether or not they have mass. What's the best explanation for a non-eternal universe? I think that the Hartle-Hawking kind of state is sort of non-eternal. It has some timeless period before that. But that might be the best one. Who's cutting the grass? I don't know. Also, that's a leaf blower, I think. Why does space-time have such high stiffness due to the speed of light? You just answered your question. The speed of light's big, the gravitational constant is small. Can you explain impulse? I had difficulties understanding it for my prof. So impulse is just, think of it as like a chunk of momentum that you're giving to something else. It's just a force applied over a certain amount of time. You apply a force for a certain amount of time, and you give the thing that you're applying that force to some amount of momentum. Why aren't we being pulled towards the closest black hole's strongest gravitational pull? We are. The strongest gravitational pull is our galaxy. So we are orbiting the center of our galaxy. How do you solve the problem of entropy in the CCC model? Well, I don't think that the CCC model is correct. But how does Penrose propose to solve the entropy problem? Ah, the rescaling. The rescaling does it, right? The entropy is essentially, I mean, the very early state of the universe, whether you're in CCC or not, is basically a uniform field configuration. And so all of the entropy is stored in the scale factor. But if the scale factor drops out, if it's no longer physically relevant, then it must be equivalent to the scale factor when the scale factor was very small. And so all of the entropy was essentially in the large scale factor. And then that large scale factor transitions to a small scale factor, and the entropy drops off accordingly. That's one way that I could think that Penrose might resolve it, but I'm not familiar with his actual solution. So intelligent, yet still believes we are on a spinning ball. Yep, because that's true. Why do geodesics change from gravity? What's the mechanism that bends spacetime? The mechanism is the mass bends. That's what the mechanism is. It's like asking, what's the mechanism that causes charges to attract each other if they're opposite charges? The electric field. Okay, what's the mechanism that causes electric charges to generate the electric field? Like that's just what the physics is. Some of these questions bottom out. Or at least we don't have the answers anymore. Will you be doing debates, or did I miss them? Not on Tuesdays and not on Wednesdays. Except on special occasions, then I kind of shift things around. What's the leading theory on where the mass of the universe that started the Big Bang came from? Trying to think of the right way to answer this, because from the question it sounds like there's some misunderstandings. The way to think about it is that, at least in the mainstream view of inflation, there is, before the Big Bang, there was just a field which was very, very high energy. And that field was everywhere in the universe. And then locally, that field spontaneously tunneled down or perhaps it did slow roll inflation, whatever the mechanism, that field started to dump energy into the other fields, which caused particles to pop out. Those particles have mass. So in some sense, the original mass came from the energy of the inflation field, the inflaton field, rather. Do neutron stars have an accretion disk? I suppose they could. In fact, I suppose they might even often do. Why is it in relativity, when talking about relativistic speeds, light delay is never even talked about? Even in Newtonian physics, it would cause huge distortion in observed speeds. It is talked about all the time. In any careful explication of relativistic effects, you always have to take into account light speed delays. How is it possible that the Earth spins exactly at the right pace and not a second or slower or faster? It does. The speed of the Earth's rotation has changed over time. I don't know what the right pace is supposed to be. Oh. Why don't, when we activate an MRI, it switch the magnetic field since it's greater than the Earth's? It does. It changes the local magnetic field pretty significantly. Does the Borel-Cantelli lemmas destroy most secular models of the universe? I suspect not, but I've never heard of the Borel-Cantelli lemma. Oh, yes, I have. It's been a long time, though. It's been like 10 years, more than 10 years even. The first Borel-Cantelli lemma, which states that if the sum of the probabilities of the events is finite, then the probability that infinitely many of them occur is 0. This result holds for any sequence of events without additional assumptions. Okay, that's not an issue. The second Borel-Cantelli lemma, which states that if the events are independent and the sum of their probabilities is infinite, then the probability that infinitely many of them occur is 1. That's not a problem either. So no? Can you explain AC and DC superposition? Yeah, so imagine that you had a, so AC has an average voltage of 0. You just take AC voltage. So if you were to average it out, you would end up with 0 voltage. Here's the 0 line, right, where this hand is. DC voltage just means that you have an unchanging voltage that's, say, 5 volts. But if you take an AC voltage and you add it to a DC voltage, you have a superposition. And so it'll oscillate around, say, 5 volts. That would be a superposition of AC and DC. I had a debate with Angel of Light. How do I debate? Oxygen needs a container. Please help me. Well, you better be able to explain gravity, because gravity is a force that can keep things in, even without a physical barrier. Why is the speed of light not infinity? It's just not in our universe. Look, some of these questions are like, why is the law of physics this way rather than that way? And like, these are questions that either don't have answers or we don't have the answers yet. From Judy Bassett with the €5, are there any subatomic particles starting with the letter Z? Not that I can think of. Did you see that according to the files, the Penrose Institute was heavily funded by JE? I didn't see that. But look, he was a billionaire and he funded a lot of science. Like, Hitler was also a vegetarian, right? Like, sometimes bad people do good things. How is energy from a windmill or a steam power plant converted to electrical? Like, what's the mechanism? Yeah, so roughly speaking, if you have something that's spinning, you can make that thing spin, say, a magnet, and then put that spinning magnet near coils of wire. And through this process called electromagnetic induction, a spinning magnet, or a moving magnet more generally, near a coil of water is going to induce electric current flow. And then you can use that to charge batteries and things like this. Oh, the Z boson. I was thinking of, yep, you're right, the Z boson. That starts with the letter Z. I was thinking Zepton, Zgwark, the Zozon. Z boson, you got me. Have you taken measure theory? I took, yes, to answer your question, yes. It was like 10 plus years ago, and I don't use measure theory very often. The Zabumafutron. Can't believe I missed that one. At what point does quantum mechanics turn from probabilistic to deterministic? There is no sharp dividing line. Do you think physics can ever explain what was before the Big Bang? Sure. It's like, it doesn't seem like it's impossible. Do you think that fields are more fundamental than particles, and that particles are just an emergent behavior of fields, or are particles more fundamental and fields are just a math tool we use? I like to think that fields are more fundamental, but, you know, I could be very wrong about that. It's kind of just a vibe. Are you still in school? No. Is there one that starts with a W? Yes, the W boson. You won't get me twice. Is the equivalence principle valid for quantum particles in a non-uniform gravitational field? The equivalence principle is supposed to always hold. Yes. It's hard to say, though, because a quantum particle is going to have a distributed wave function, right? These are the kinds of questions that we don't know the answer to. Can you explain killing vector fields in differential geometry? Yeah, so a killing vector field is merely a field that generates isometries, right? What that means is that if you take the derivative, the Lie derivative of your metric, with respect to your killing vector field, you get 0. In layman terms, what that means is that if you travel along that vector, you won't really notice that your space-time is changing. Or if you're talking about a Riemannian manifold, if you travel along that vector, your Riemannian curvature quantities, like your scalar curvature or your Kretschmann scalar, all of these quantities will be unchanged. If you move along the integral curves generated by your killing vector. How do you get your mind to stay sharp the whole day? I don't. I struggle. Is redshifted light still traveling at sea? It is. What's your thoughts on the theory that we are already in a black hole? I don't think that we are, and I don't think that there's compelling evidence that we are either. Are you involved in any research regarding gravity, like testing for quantum fields? Well, it doesn't sound like you're talking about research regarding gravity. Yes, I do research in gravity, but not quantum stuff. At least not often. Man, I'm hungry. What's the difference between a Riemannian manifold and a pseudo-Riemannian manifold? It's just the signature. It's the sign of the eigenvalues of the metric is one way to put it. The metric is viewed as an endomorphism, of course. Or no, I should rephrase it. I'm sorry. It is it's the signature. So you can always diagonalize a matrix, right? And so actually, no, my first statement was correct. You can just treat it as an endomorphism, and then you can look at the signs of the eigenvalues. No, that's still wrong. That's still wrong. No, you want to treat it as a matrix, even when it's just a metric and not the Kronecker delta. The eigenvalues of the matrix, or the entries of the matrix, will tell you, once it's diagonalized, what the signature is. If you have -1, then it's pseudo-Riemannian. If you have all ones, then it's Riemannian. I'm going to end the live soonish, and then I'm going to go eat a snack. Don't worry. Does that mean spacetime would be Riemannian if the time component had the same sign as the space components? Yes, that's exactly it. Introducing the time component makes things a lot more complicated, but it also makes solving the differential equations or understanding the differential equations a little bit easier. Hello, I'm relearning math and physics chemistry from the start for my PhD so I can understand things, not just do calculations. Any advice sources or books I can use? You'd have to give me a lot more details because, like, I need to know what you need to know. You didn't even tell me what your PhD is. Do physicists use the exact gravitational force or the rounded? Physicists just use the letter G if they use it at all. What dictates C? Why that specific speed? Well, it's only that specific speed because we use specific units. In another set of units, it's just 1. Please reveal our community gift. You can find it by tapping ... live gift. Well, look, I'm on the computer, so I don't know if that's a thing I can. From Nectu with the $5. Thanks for the bonus stream last night on Ian's live. That call was a doozy. Yeah, it was. It really was. I want to go more in depth when it comes to neuro and comp science. How much physics should I know? I don't think that you need to know much physics for either of those. You measure the probability of a wormhole forming on a Riemannian manifold. Well, you'd have to first, like, do you mean like in a quantum sense? Then you'd have to do like quantum gravity stuff, which we don't have a good handle on. You explain the Boltzmann distribution? Oh god, I can never keep these things straight. I'm gonna look it up and then I'll explain it. Yeah, okay, so the Boltzmann distribution is it's a particular distribution about energy, about the probability of finding a state in a given energy with certain, with a given temperature. So that's all. It's a thermodynamics thing. If you don't remember, by the way, I hate thermodynamics. Like, I hate it so much. So I guess the point is that the probability, if you have so for Boltzmann distribution, let's say that you have a whole bunch of particles with whole bunch of particles that make up an object or make up a system with temperature T, right? The probability that any one of those particles will have a certain amount of energy is given by a Boltzmann distribution. That's the main idea. And so at any given temperature, if you have a large enough system, the odds of finding a given particle at some arbitrarily high energy is not 0, but it is very, very small. Whereas the odds of finding particles with lower energies will be higher. Oh god, my stomach is just rumbly. All right, y'all. I think I'm going to end the live stream here. I need to go eat a sandwich or something. Sorry for the slightly short live. I will see you guys tomorrow for some more debates. Until then, make sure to take care of yourself. Make sure to join the Discord server if you're 18 years or older. And I'm going to read one more super chat. From Optopoppet with the $5. If I recall correctly, the universe is mathematically flat, but time is perpendicular to all 3 axes. Does that make the universe a Klein bottle? No, the universe isn't a Klein bottle. Klein bottles are still 2-dimensional. No, it just means the universe is 4-dimensional. Right. Okay. I'm going to go make myself a sandwich or something. And I will see you guys for some debates tomorrow. Make sure to join the Discord server and make sure to go subscribe to the debate channel on YouTube. It's at Dr. Blitz Debunks. Go subscribe.